attention to quantum complexity by Eun-Ah Kim. Sorry about my pronunciation.
Well, can you hear me? Is microphone working? It's supposed to be working, right? Yeah. Okay. All right. Well, thank you for the invitation. It's been really interesting to learn from people working on very broad set of topics. I want to talk about attention to quantum complexity. I'm Eun-Ah Kim at Cornell, and I'm a quantum many-body theorist. Most of my career, I've been interested in trying to understand how to think about data from solid-state materials. But all along, my focus was always about how do I understand what is going on in nature by starting from data and try to understand how to think about it, meaning getting theoretical insight, and see confirmation of my insight by trying to be predictive. Nowadays, quantum simulators are a new platform where we can sort of try to emulate or simulate nature with some controlled models. But in all of these cases, if you really care about trying to understand what is going on from data, often there can be sort of data-driven challenges. For about 6-7 years, I've been trying to find ways of embracing machine learning to make progress. So today I want to specifically talk about data from quantum simulators. So projective measurements. This is a famous experiment by Stern and Gerlach. This is the plaque that's celebrating their experiment. And here is how they were able to study, or rather they were able to purify from in today's language. They take a mixed state of silver atoms in oven, high temperature, so it's in a mixed state, and you put it through this incoherent magnetic field, and it would come out in one of the two possible states. This was a way of doing a projective measurement and purifying a mixed state into spin up and down for a single spin. Fast forward to today, instead of projective measurements on single spin, we can now do measurements on a lot more spins or qubits. But still, you might have intentions of realizing a certain state. The only way you can interface with that system, that physical system, is through measurement. So then, if what you have is a density matrix, and what you get to see is this measurement, there is a natural question of how do I go from what I can see to what I might have. Now, we are approaching these questions of this sort using attention mechanism. So let me just give you a brief kind of primer on what attention mechanism is and why would that be interesting. So attention mechanism is a core mechanism in the language model, large language models, such as ChatGPT. And it works in a way that is somewhat different from, say, neural network. So here is a sentence. He lives in the White House. In order to understand the meaning of this sentence, you not only want to know the meaning of each word, treat it as an element of a vector, but you actually want to know how to think about different words together. So you want to really think about the word white and house together, and that will influence how you think about the word he. And the way attention mechanism accomplishes considering different elements of this sentence as a vector together, even when the words are far apart, it depends on the structure of the grammar of your language, is by letting these transformations called query and key. These are linear transformations. It's a rotational vector. So you would rotate the sentence one way and rotate another way. And you try to find this matrix, Sij, that's this attention score. You try to find the attention score that maximizes the performance of the model. And that way you can try to take words into account together, even when the words are far apart in the sentence. Attention mechanism takes this non-locality to extreme. It actually, in the purest setting, attention mechanism operates in a way that you actually don't care about the location of the word. Now, in reality, you do care about the location of word to some extent, and that can be implemented through doing some sort of positional encoding. So now, how could this be useful for thinking about quantum state data? Well, if you have a many-body quantum state, maybe there is some non-local entanglement. So you might want to care about spins at different locations. Also, if you have a quantum state where you are looking at these projective measurements, you might actually want to know how to think about one measurement in relation to another measurement. So we had this vague idea that maybe this large language model, which was revolutionary in thinking about language, which is a problem in large dimensional space, maybe we can use that to try to learn that probability distribution. What do I mean by probability distribution? So I have a density matrix, that's my state, but I don't always get to know what it is. Now that density matrix would be in a basis of bit string. I can think of it as a probability distribution. This is just what you learn in quantum mechanics. So generative modeling in the language sense is to actually try to learn the probability distribution so that you can generate the next data. That's how ChatGPT operates. When you ask a question, it would say something. It's generating data based on probability distribution. It kind of learned to model from lots of simulating data. Lots of the data that was used for training. So the idea is, can we try to do this generative modeling? So that was our first attempt in this paper. And what we tried in this case was we had an idea that, well, maybe actually we really care about entanglement or correlation between different qubits. So we're going to take each bit as a token. Token means entry into this vector, element of a vector. And we tokenize each bit in a string. And that's how we try to learn. And that was this attention-based quantum tomography idea. We would take positive operator valued measurements, lots of measurement data from IBM quantum computer. And then we try to learn the probability distribution using the transformer architecture. And from that, we would invert and try to model the density matrix. Now, this was sort of following what was very sort of a growing interest in the community, small community of people who were trying to find, trying out, exploring application of machine learning on quantum state data. Generally, there was a lot of interest in trying to do generative modeling, and that's what we tried. The only thing that was different in what we were doing compared to what other people were doing was that we were trying to use this transformer architecture. So it was, semi-successful compared to the leading architecture at the time. Now, this was a couple of years ago, which in this world is kind of eons ago. At any rate, at this time, the leading architecture was recurring neural network, which is another language model, RNN. And compared to RNN, our AQT required much fewer measurements to reach the same sort of classical fidelity. However, when we try to push this on the experimental data, what we found was that the left-hand side is the MLE tomography offered by IBM Qiskit. The right-hand side is what AQT did. And if you compare the two, they look similar, which means it's AQT was working, but it's not like there was a magical sauce that allowed AQT to beat the exponential wall. The exponential wall is an exponential wall. There was no way to really beat exponential wall and get better scaling with tomography. So that was irrespective of the positive note we tried to take in the paper, in reality it was a defeat. So what did we do then? What we realized is that it's a very simple fact of life. When you try to know a lot, you might need a lot of data. So, if having all the data that you want is not afforded by the fact of life, what can I do? I can be less greedy. I can start asking, so what can I try to do that is asking for the least, but nevertheless a meaningful amount of information? So that's our new approach. That's take two. And that's what I want to really focus on the rest of my talk. So after this defeat, we regrouped ourselves and we thought, okay, first of all, we should know what we are after. And we should have a good reason why what we're after could be reachable. What do we want to learn? We decided because doing tomography is not doable, and also not even learning the probability distribution to the full extent is not something that we can reach. We're going to lower our bar, but nevertheless try to learn something useful. And that something useful is broadly going to be couched as quantum complexity. I'm going to get to a specific definition in a bit. Then the next thing is what data would allow us to learn quantum complexity. More specifically, precisely what we are after is large moments of the distribution. I showed you the distribution. Large moments of the distribution is what we're after. And if we want to learn the moments of the distribution, we would have to attend between snapshots. That is, we have to take the snapshots themselves as token instead of the data at individual bits. So what is quantum complexity? Well, if you want to say something is complex, common sense is that you have to define it with respect to something else. So complex compared to what? One way to define quantum complexity that I've been told is sort of it's been very productive way in the quantum gravity community is to think about if I have a pure state psi, I'm going to ask, what is the minimal circuit depth of unit rate that I need to get to that state, starting from some simple reference state? That could be some product state. So if there are multiple different ways to arrive at the same state, I am interested in the minimal depth. And the depth is going to be a measure of complexity. How do you prepare a complex state? So if you want to get to a very complex state, this was a subject of a great deal of research for the last several years, where people have been interested in using random circuits to prepare a complex state. And Nicole and collaborators have proved the conjecture in this paper, where complexity grows linear in depth until it saturates, as complexity defined above here. So now that's all really nice, but so this is a rigorous, theoretically very useful definition, but it's not always easy to figure this out if somebody hands you a state, and rather if somebody hands you a bunch of data. Especially when that bunch of data is coming from a mixed state, as the real systems are, it can be much more challenging to go after this. However, there is a way to make contact with sort of theory of statistics, given that ultimately there is a probability distribution we have in mind. We can think about moments of distribution. And this was, on one hand, very unfamiliar thing for me personally to think about. I hadn't thought about moments of distribution until this point, because everything we learn is Gaussian, and Gaussians only require you to know two things. You don't even call it moment. But if you talk to anyone who's thought about probability distributions, which a lot of data scientists have been thinking about, for them, whether they know any quantum mechanics or not, many of them don't. But if I say, I want to learn distribution, they take it to be a very natural thing to start asking about moments. They say, well, can you learn moments? And turns out this idea of thinking about moments is something that people have actually thought carefully about. So if I want to learn some aspects of this distribution that I am going to sample, and I cannot know the full distribution, but perhaps I can access some amount of information about the moments. And that's going to be my goal. Now, how is the moments of this probability distribution in the bit string basis, measurement basis, related to the unitary? you can rewrite this probability distribution as a trace of the density matrix with insertion of the measurement in the middle. And you can see that the moments of this distribution, if I raise this to power k, it's going to be looking at the unitary U dagger and U both raised to power k. And for the random circuit, it was found that people have carefully studied that there is a notion of approximate k design. That is, you compare moments of this unitary raised to the power k to reference here, in this case, Haar random. And when you can match the Haar random to up to some kth moment to arbitrary precision, that is called approximate k design. And this k can be treated as a bound for complexity. The complexity that we have abstractly defined at the beginning, this is how many steps of the circuit that you need. So from the complexity theory of the random circuit point of view, this moment is an interesting thing to study. But even if you don't know that, if you just look at the data and you know the basics of quantum mechanics, that, okay, there's a probability distribution, trying to access moments is still a very meaningful thing to do. Specifically, what we are used to doing, when somebody gives you a whole bunch of data that has to do with, snapshots, the first thing what you would do might be averaging it. Maybe you'll be averaging for a particular quantity, and that averaging means you're looking at a quantity that's linear in the density matrix. That's what it means to average. But you might be interested in fluctuations, quantum fluctuations, and you might be interested in quantities that are nonlinear in the density matrix, such as entanglement entropy, or something to do with topological order, which does not have expectation value. So for all these reasons, it will be interesting to study moments, higher moments of the distribution. How can I study higher moments of the distribution when I cannot sample infinite amount? Well, the way how transformer architecture works is such that it's a matter of what I treat as a token. If I tokenize each snapshot, then I can try to learn correlation between these snapshots. And this is called self-attention. Each layer of self-attention is looking at pairwise correlation. If I stack that up, I can get to higher moments. So that's exactly what we did in this paper. You can find more details of the work in this in the preprint. This was a collaboration between my group and several other groups. This was a sort of an outcome of long-standing collaboration between my group and Kilian Weinberger's group, who is a computer science faculty at Cornell, and we've been collaborating for several years now. And we had the fun of collaborating with people at Google and MIT who has generously shared their data with us. This work was really spearheaded by my student, Haejin Kim, who is actually here in the audience, Yi-Ching Zhou, who will be graduating next summer. So she's applying for jobs this fall. She's awesome. I just cannot say it enough. She's just amazing, incredible. And Yi-Chen Shu, who is a postdoc who's been working with me in my group for about a year. And it's been really incredible how people with very different backgrounds came together and make this monster of a project possible. So what are we after? We're going to try to distinguish data from two different states. How do we know they're different? We think that they can be different because the way they're prepared is different. For instance, you might be looking at a state that has that could have different scaling of entanglement entropy. You could be looking at states that are prepared to be toric code, but disordered to different degrees. And importantly, the random circuit at different depth. We would be looking at data from random circuit at different depth. And as you increase this random scrambling circuit deeper and deeper, what you end up having is you start exploring more and more of your 2 to the n dimensional Hilbert space. 2 to the n possibilities all start showing up. And the challenge is very pragmatic and real and like very current. That is, I have just a bag of data, and my job is trying to figure out what can I learn from this bag of data. So the architecture that we've used that was really very much guided by what we are after is what we named Quantum Attention Network, QAN. And it starts with the input. An important thing about the way we treat the input is that we wanted to learn correlation between or moments or some approximation of moments between different snapshots. So the input could not be a single snapshot. We collect a set of snapshots into a set. We batch them. So now we take all this lots of measurement data, we batch them into different groups. It was also important to realize that the order in which the snapshots come couldn't matter. So the data had to be treated with permutation invariance in mind. Some sort of simple lessons that I've learned trying to do this sort of, I don't know, it's the first time we try to do something like this, was that, it always pays to think about what you're doing. It always pays to think about what is the structure of what you've got. It's very kind of common sense, but thinking is hard. So, you can be tempted to just go start working and then try to, put off thinking until last minute. Bad idea. We've learned it hard way after, spending almost 6-7 months failing. But eventually we got to the right thing. So the right thing that we eventually got to was to recognize that, okay, we want to treat this snapshot as a set element, permutation invariant, not like a sentence. In a sentence, order actually matters, but with the snapshots, the order shouldn't matter, and that made a big difference. And then what do we do? Once we have data prepared the right way, we put it through encoder, part of the architecture. This is, encoder is sort of what machine learning people call sort of this part of what's going on. This structure of this encoder is to really try to learn self-attention, that is looking at attention between the snapshots. But we are working with, for 36 qubits, we were working in lots and lots and lots of data. And as we try to go to higher and higher order of self-attention, it became challenging to do it in the brute force way. So we had to come up with sort of resource efficient way of attending to high order, because that's what we were after. But in a way that we can keep the complexity of this is computational complexity of the model sort of under control. So that was Miniset SAB. SAB stands for self-attention block. Miniset SAB is what Chow and Jin, Killian's students, have devised for us. Once we go through, but this whole thing is a function. We all know what a function is. Function is a map. I take data, there will be an output. So we have to go through this whole step, but eventually I have to simplify so that I get out to an output. And that step of condensing everything is what's happening in the decoder. In the decoder, something additional sort of attention mechanism that we implemented was giving the architecture the ability to be discerning about data. So we let the architecture sort of put more attention or less attention to some part of the data as it sees fit. So all of these things, all of those parameters of the architecture are something to be learned. But at the end of the day, there is an output. What does the output mean? We've phrased everything as a classification or discrimination problem. Now, discrimination problem, in the olden days when the convolutional neural network was new, people all knew about cats and dogs. That's an example of a discrimination problem. It's the simplest kind of machine learning task that we can devise. And one of our referees said, you should be doing generative modeling. And I'm like, where have you been? We've been saying that's way too hard. If you want to go to scale, you have to think of a simple problem. So we're doing a discrimination problem between two bags of data. So this output is a confidence for the machine would spit out saying, well, you've trained me with two bags of labeled data, and you're giving me this new data. this is the confidence by which I think this data belongs to your first bag. So that's the output. We give all this data. At the end of the day, there will be one number. Okay, how much time do I have left? 5 minutes. Okay, so we've covered 3 different problems in 5 minutes. 10 minutes. Oh, that's better. Okay, I can give 3 minutes each problem. So the first task that we put the machine through is witnessing the entanglement transition. Maybe this could be a crossover, but it matters less whether it's crossover or transition for us. It's about whether we can tell them apart. So the challenge is that you might have various settings in which that you think the entanglements will be volume law, that is like very entangled everywhere, versus entanglement is area law, that is sort of more local. And this notion of different entanglement scaling shows up in many different settings, such as measurement-induced phase transition, etc. We were interested in approaching that problem in general, and we were specifically interested in trying to learn this from experimental data. Now, what you can do is to calculate entanglement entropy from data. You can do so by either doing subsystem tomography if your system is small, or you can try to estimate the entanglement entropy using shadow tomography. But both of those have costs. That is, you have to at least have multi-basis measurement for tomography. Subsystem entanglement entropy calculation requires, essentially, you need to actually to calculate, you need to do the tomography, and that's expensive. And what we wanted to do was something that is easy for those who are doing the measurement. We wanted, we didn't want to ask people to produce 2 copies, like for instance for Rennie, and we wanted just a computational basis measurement. We wanted to see what can we do with what is most accessible. And the reason why this could work is even if we give z-basis measurement data only, by relating between z-basis measurement, for instance, in comparing these 2 snapshot data, the way that the 2 are differing really has to do with the correlation of X, because that's the flip. And we thought, so maybe our architecture through attention can learn change in entanglement scaling. The specific use case that we've turned to is this hardcore Bose-Hubbard model. Will Oliver's group have realized this in experiment. And what they were able to do is to get to not a pure state or a ground state, but what they called coherent-like state. That is, at a given parameter setting, written as delta over J, they would always have a superposition of different states, different eigenstates of the Hamiltonian. But what superposition you have depended on the parameters, such that when the delta over J is small, they knew this follows volume law. When delta over J becomes large, it sort of becomes area law. How did they know? Well, they actually did the hard work of calculating subsystem, doing the subsystem tomography and calculating reduced density matrix. Instead, what we wanted to do was to not work with the subsystem data, but with the full system data and just the z-basis measurement. Now, first, we try the model that does not have attention. Now, if you are paying attention, you can pat yourself on your shoulder saying, okay, I paid attention to that talk. If you understood at the end of the day that there are a couple of words that keep showing up. The one word that is going to keep showing up is attention, self-attention. So this is architecture that does not have self-attention, this multi-layer perceptron. We always make sure the computational complexity of these models are the same number of parameters. That's how we know the architectural design is what made the difference. It's not the matter of parameters. So when we just use the architecture without the attention mechanism, we were failing. How do I define failing? Well, if the confidence is 50%, that's a coin toss. It's randomly saying, well, I think it's 1, I think it's 0, 1 is volume law, 0 is area law. But once we introduce one layer of self-attention block that allows the model to see the second moment, we started to see the difference between, and if we make the set size large enough so that you have large enough sample to try to estimate the moment, as we make the set size larger and larger, we found the confidence go up for delta over J0 to be a volume law and high value to be area law. And by increasing the self-attention block number, we were able to sharpen this transition. And this was important because we had a benchmark. This was a benchmark example. Now I'm going to go through the complexity of deep random circuit. Now this was a problem that became famous as people were pursuing the quantum supremacy in this setting. That's not my fight, it's somebody else's fight. What I'm interested in was, can I tell the depth becoming deeper as I look at the data? And the problem is that you have this large space that is all being sampled, but even if this is the distribution, this is the data you have. So once again, our Quan was able to tell the different depths. And but before I get to say how Quan is successful, I have to once again show how other approaches didn't work. And this is not to put down anybody else, it's really us. We tried many different things and we were having several fantastic months of failing and failing and failing until we started to use the Quan architecture. So what is the task here? We are trying to see whether we can learn to distinguish depth 4 from depth 20, depth 6 from depth 20. Deeper depth for up to some saturating depth was supposed to make the state more and more complex. So can I see that from data? Now, cross entropy benchmark was a conventional measure which really requires comparing the data to simulation and to the completely random setting, but it kind of limits how far you can go. And this is Quan's accuracy. Year and a half of toiling becomes one plot. Something that we are highlighting here is compared to linear XAV, we were able to go deeper. And you can see that the increasing the set size mattered, and this is how the learning was scaling as we go to larger system sizes. Now, that was all on the experimental simulated data without noise that you can learn as you get deeper up to depth 10 that your system is approaching more like really deep limit. Now, when you go to the experimental data, linear XEB was learning most of the noise evolution, but the Quan that was trained on simulation data was able to extract aspect of this experimental data that resembles the pure state evolution that we are after. Now, I think I'm really out of time, so I'm going to kind of skip over this third application rather quickly. Here, we are after looking at toric code, the leading approach to error correction code that is being really pursued. And we were interested in seeing when we increase the error, can we learn that the system is losing its topological order? Here, once again, we had benchmarking. So as we for set size 64, this is the result of Quan. And what we knew from rigorous theory is two axes of disorder. So this is one type of noise that's incoherent noise. This is another type of noise. The Quan's learning based on training between these 2 points, first of all, saturates the known bounds. It also transfers what was learned here to this phase boundary. And it, for the first time, provides boundary in the middle, which was not known before. Now, I don't think I have time to go over why this is working, but I will just say that there was this pooling attention was used to really focus on the large loops that are more visible in the topological order where the loops of all size is supposed to occur. So my time is up, and I'm just going to leave you with this summary slide where this is the sort of a caricature of the architecture, and these are 3 applications that we've tried. But there were several lessons that we've learned from this. Always in retrospect, it's kind of obvious Now, you've worked hard to set up a system and you take all this data, which embodies quantum fluctuation in them. It also embodies the imprints of noise. Now, you cannot tell a mixed state and pure state apart from just the linear, the diagonal elements of the density matrix. But the moment you look at density matrix square, you can tell them apart. So the point is, if you don't remember anything else, I would like you to take away that by taking these snapshots, fluctuation seriously, and try to take data, the snapshot to snapshot fluctuation into account, we should be able to access a lot more of the information in the whole data than we would by taking averages. That's kind of obvious. So then what I can provide, what I'm bringing to the table is this attention mechanism, quant architecture, was designed to be able to do just that in an effective way, in a way that is kind of agnostic of specific quantity that you're after, and works even for a most challenging problem of random circuit. Thank you for your attention.